This video is an introduction to solving exponential equations. Before we really begin solving exponential equations, we need to review some basics about exponents. So to start, a term that has a base and an exponent looks like this. 8 to the power of 2 is how we might read that, or 8 to the second power, or even 8 squared. The 8 part of this is the base, and the 2 is called the exponent, or sometimes referred to as the index or the power. The exponent of a number says how many times to use it in multiplication. So 8 to the power of 2 means to multiply 8 twice. So 8 times 8, which is 64. So an exponent just saves you writing out a lot of multiplies. For instance, a to the power of 7. It doesn't matter that there's a variable, a letter as the base. It still means that you're multiplying that thing by itself 7 times. So it's a times a times a times a times a times a times a, and there are 7 of those. And you know that when we multiply variables, we often don't write the times symbol in between them. We just write them next to each other. The following are some laws that we'll use in the next couple of days. These are exponent laws, things that we agree on the notation and definition of. For instance, anything to the power of 1 is equal to the thing you started with. So for example, 6 to the power of 1 is 6. 8 to the power of 1 is 8. Z to the power of 1 is Z. Anything to the power of 1 is itself. The next thing that we all agree to be true is that x to the power of 0 is equal to 1. Remember that in algebra we use x to signify any number. So it doesn't matter what the number or letter in this case is. If it's to the power of 0, the whole thing is equal to 1. So 7 to the power of 0 equals 1. Negative 8 to the power of 0 equals 1. 5,337 to the power of 0 equals 1. M to the power of 0 equals 1. So anything, absolutely anything to the power of 0 is equal to 1. These next two are related. It's the negative exponent rule. It says that anything to the power, I'm going to skip to this one, of a negative number is equal to 1 over that thing to the positive power. So it's going to be important when working with exponents that an answer never contains a negative exponent. And so the way that we handle that is by saying anything to a negative power, for instance, x to the power of negative 3 is equal to 1 over x to the positive 3. And so it's for us to get rid of the negative exponent. You just take 1 and you put the thing you started with in the denominator with a positive exponent. So the last rule is going to be when you have what I call a power of another power. When we have some base x raised to a power, and then that's in parentheses raised to another power without another x or any other letter out there as a base, the rule is to multiply the powers together. And you're used to seeing parentheses and thinking that you have to multiply things like distributing. And so we're sort of doing the same thing with an exponent right outside of parentheses. Look at the example here. We have x squared, and then that's in parentheses to the power of 3. And so what we do is we take the 2 that's inside the parentheses as an exponent, and the 3 that's outside the parentheses as the exponent, and we multiply those together to get x to the power of 6. Now, most of these rules are not going to come up for another day or so, but you need to be familiar with them because you might be asked to just practice them a little bit when you're in class. Okay, exponential equations. An exponential equation is one that a variable, occurs in the exponent. And we've seen that already in this course. So you've learned to graph an exponential equation. Now we need to learn how to solve an exponential equation when there's one variable involved. If the exponential equation has the same base on both sides of the equation, we can use this rule and set the exponents equal to each other. Because if the bases are the same, and the left side has to equal the right side, doesn't it make sense that the exponents also have to be equal to each other? So I sort of like to box in those exponents. If the bases, the 3's in this case, are the same, the exponents have to be equal. So x has to equal 6. If you look at this other example here, we also have an exponential equation where the base on the left is 47 and the base on the right side of the equal sign is also 47. And since those bases are the same, then whatever their exponents are, they have to be equal to each other. And so the x plus 4 has to be equal to the 9. So if x plus 4 equals 9, and we subtract 4 from both sides to solve for x, then of course x is equal to 5. Now the rule here only applies if the bases are the same. And for today, we're only going to look at problems where the bases are the same. So let's look at the example on this screen. First, the pre-typed one, 7 to the power of 2x plus 1, if you can't read it, is equal to 7 to the power of 3x minus 2. Since the bases are the same, notice the base is 7 in both cases, then we take the exponents equal to each other. And so again, I like to box them in just so that I focus on them. The 2x plus 1 equals the 3x minus 2. And here's my equation. And you solve this equation using the normal steps for solving linear equations, and you get 3 is equal to x, or x equals 3. I want you to pause the video and try this one on your own. Okay, 8 to the power of 2x is equal to 8 to the power of 20. You always need to verify that the bases are the same, and as long as they are, you can make the exponents only, you're not doing the base here, it's hard to box that in, equal to each other. So the 2x has to equal 20 if the left side is going to equal the right side of the equation. Well, if 2x equals 20, and I divide, of course, both sides by 2 because I want x by itself, then I get x is equal to 10. And you can verify your work, as with solving any equation, by taking that 10 and plugging it back in for the x. 2 times 10 is 20. 8 to the power of 20 equals 8 to the power of 20. And obviously that has to be true. So tomorrow you're going to be doing some equations where the bases aren't the same. And to be able to work with those equations, there's some things that we need to review and make sure are familiar to you. So I'd like you to take a look at the pattern below. 1 squared, that's 1. 2 squared, or 2 to the power of 2, is 4, because it means 2 times 2. 3 squared doesn't mean 3 times 2, remember. The exponent tells you how many times to multiply the base by itself. So this means 3 times 3, which is 9. And you can do these in your calculator by using the squared key, which is right to the left of this, which is directly to the left of the 7 on the TI-30XS. 4 squared is 16. I'd like you to complete the next few, 5 squared, 6 squared, and 7 squared. And you probably need to be fairly familiar with these answers, the ones in red here, that are called the perfect squares. 5 squared you'll see is 25, 6 squared is 36, 7 squared is 49. And if you keep going, 8 squared is 64, 9 squared is 81, 10 squared is 100. These are perfect squares, and it's convenient for these to be very familiar to you so that you can come up by working backwards with what number squared it is. And you'll see why that's important tomorrow, but for now, try and get yourself familiar with the answers here. The same thing can be done for perfect cubes. It's not as important that you memorize them as much as recognize when something is a perfect cube. Perfect cubes are powers of 3, and it might be more necessary for you to use a calculator here than it was with the perfect squares. You'll see that 1 to the power of 3 is 1, 2 to the power of 3 is 8, 3 to the power of 3 is 27, 4 to the power of 3 is 64, and you'll notice that 64 also comes up as a perfect cube. As a perfect square. 5 to the power of 3 is 125. 6 to the power of 3 is 216. And 7 to the power of 3 is 343. Now you can keep going with these, but I will tell you that you are most likely to see 1, 8, 27, and maybe 64 come up in this course. We don't expect you to recognize off the top of your head really beyond that in the perfect cubes. For perfect squares, it's expected that you will recognize all of them up to 10 squared at least, and maybe even up to 12 squared. So practice those in your head. You're going to need to be able to rewrite a number as something squared or cubed. So the perfect squares, 1, 4, 9, 16, 25, 36, 49, from there 64, 81, 100, and of course you can keep going. Alright, so in my example here, if you have 25 in your problem and you need to express that as something squared or cubed, you can look at your list or hopefully recognize that without having to have the list written down as 5 to the power of 2 or 5 squared. And 8 isn't something squared because you can do the perfect squares and see that 2 squared is too small and 3 squared is too big. But 8 is equal to 2 cubed, or 2 to the power of 3. So using the list that we've made, and I've circled the perfect squares in red and the perfect cubes in green, I want you to try a few. Pause the video and try these on your own. All right, how'd you do? I hope you took a look and saw that 81 is actually 9 squared. And 27, if you look back at your perfect cubes, is 3 to the power of 3, or 3 cubed. And 36. 36 shows up in our perfect squares as 6 squared. And so write these out even a few times. Become familiar with the number so at least you know it is one of them, and even if you have to work through the list, it's going to help you to solve these exponential equations more easily if you're familiar with these perfect squares and cubes.